Okay, I'd like to, like the other speakers, thank the organizers for inviting me. My talk today is going to be on the subject of the Ryu-Takayanagi holographic entanglement entropy formula. And I think many of us think that this formula contains within it some deep message about the nature of space-time in gravity. And the purpose of my talk is hopefully to take a step in the direction of decoding that message. This is the outline. I'm going to start out by basically expressing some confusions, explaining some conceptual puzzles that have always troubled me about Ryu-Takayanagi formula. And basically, they sort of can be summed up in this question, how should one think about the minimal surface? What's the role of the minimal surface? And in some sense, the question, the way that Juan posed it at the very end of his talk, where are the qubits? So what I'm going to do then is I'm going to actually propose a reformulation of Ryu-Takayanagi, which I will argue in the third part of the talk actually resolves these conceptual puzzles. And I probably won't get to it, but there are also some extensions of this picture. And I think that this picture kind of points, the picture that I'm going to explain kind of points to a new way to think about the connection between geometry and information in gravity and the holographic principle. Okay, so I'm actually going to start with an important precursor to Ryu-Takayanagi formula, namely the Bekenstein-Hawking formula. And if you ask this question, why is the entropy proportional to the horizon area? Well, one kind of obvious answer that pops into mind is simply that for some reason the bits which encode the microstate of the black hole, of which there are s, up to some factors of log 2 that I'm going to ignore in this talk, are actually distributed, are localized on the horizon at a density of 1 bit per 4 Planck areas. And in fact, if you do a Google image search on Bekenstein-Hawking entropy, or I guess here if you do a Bing image search, you'll get a lot of pictures like this one, where you see these bits spread out on the horizon. Now, I think one of the most important conceptual lessons we learned from Ryu-Takayanagi is that actually this relation between surface areas and entropies, which was discovered by Bekenstein and Hawking in the context of black holes, in fact has nothing to do with black holes. It was never about black holes or horizons or any of that. It's far more general than that. And that actually creates problems if you want to believe in this sort of naive picture that the bits are located on the horizon, because whereas the horizon, you can certainly say a black hole is a very special kind of object and the horizon is a special place in the space-time. In Ryu-Takayanagi, the minimal surface, whose area tells you the entropy, is just some random place in the space-time. And one of the features that you have here that you don't have with Bekenstein-Hawking is that you have a new degree of freedom, namely the choice of your region A. And as you move A, the minimal surface moves. And that is what's going to lead to some of these puzzles that I'm going to explain. Not only does it move, but in fact it can jump. And so there are these well-known phase transitions in the position of the minimal surface in the entanglement entropy. So in this example, what I'm computing is the entanglement entropy of the union of two separated regions, A and B, and as I change the separation, the minimal surface will swap from one locally minimal configuration to another. And so that leads to the question, well, where were if you want to believe that the bits are somehow associated to the minimal surface, were they here or were they here? And in particular, if I actually sit on the phase transition point where these two competing minimal surfaces have equal area, then you would have to answer that question, are they on one surface or the other or both? And that suggests some kind of non-locality in where the bits are. And to sharpen that, another thing that kind of always confused me is when you look at these quantities which encode basically the structure of the state. You compute them by taking differences of areas of surfaces that pass through different parts of the bulk. So here I'm talking about quantities like the conditional entropy, the mutual information, and the conditional mutual information. And let's just remind ourselves of why these quantities characterize the state. Just first classically, which is the simpler case, you can line up the bits of A and B in a compressed encoding so that it becomes clear that the bits of A can be divided into two subsets. One subset are the bits that are purely in A, and the other are the ones that are shared with B. And the number in the first subset is the conditional entropy, and the number in the second subset is the mutual information. Now, quantum mechanically, you have entanglement, and things are more complicated. This is just sort of the simplest kind of thing that can happen, where you have maximally entangled pairs of qubits. But in general, the entanglement will decrease the conditional entropy, and in fact can make it negative, which is a sure sign that you have entanglement. This can't happen in a classical system. But the point I'm trying to make here is, so let's say we go back to Ryutake Yanagi, and now we have a surface for A in one part of the space, a surface for B in another part, and the surface for A union B in some other part. And somehow the differences between the areas of these surfaces is supposed to tell me how many bits of A are purely in A and how many are shared with B. So again, that suggests some kind of non-locality. The conditional mutual information is just a more complicated one, which I'll come back to later. But roughly speaking, what it tells you is just like the mutual information tells you the amount of correlation between A and B, the conditional mutual information tells you the amount of correlation if you condition on the state of C. Okay. And then my third complaint about Ryutake Yanagi, which is clearly related to the other one, is so we have this proof that it obeys this important strong subadditivity inequality, and the proof is fairly simple. For example, in this kind of simple setup, it basically reduces again to basically saying that this area plus this area is more than this area plus this area. So again, we're comparing areas of surfaces passing through different parts of the space and making a very simple argument that that difference is positive. So that's nice, but the thing that I've never understood, or that I've always found kind of unsatisfactory about this proof, is that while it tells us that Ryutake Yanagi satisfies strong subadditivity, it doesn't really tell us why. And strong subadditivity actually has an information theoretic meaning. It has many information theoretic meanings. One of the simplest is just monotonicity of correlations, that A is more correlated with BC than it is just with C alone. Okay, and yet I've never been able to see a connection between that simple meaning of strong subadditivity and the proof that Ryutake Yanagi obeys it. Okay, so what I'm going to do next is I'm going to simply rewrite the formula in a new way. So I'm not going to change the formula at all. It's going to be exactly the same formula as before, just rewritten in a new way. And I think you'll see that once you rewrite it in this new way, then these confusions just kind of melt away. And the basic thing I'm going to do is I'm going to just eliminate the minimal surface. So in the new way of writing the minimal surface won't appear. In fact, there will be no surface areas. Okay, and in fact, I'm just going to deny that there is any deep or fundamental connection between surface areas and entropies in gravity. The connection that there is just going to be a derived or sort of circumstantial one. And I hope that this new picture, this new version of Ryutake Yanagi will suggest a new way to think about, as I said before, the connection between space-time geometry and information, and about the holographic principle. To do that, I'm going to need a simple theorem from differential geometry. Actually, this theorem is originally from network theory, and it's one of these statements about minimal surfaces, which is pretty easy to convince yourself that it's true, but very hard to prove. And I'm not going to bother with that part. I'm just going to state it. So to state it, I need to define something called a flow. A flow is simply a divergenceless vector field whose norm is ever less than or equal to 1. Oh, by the way, so we're on some Riemannian manifold with boundary. And it's very useful, actually, to think of the flow in terms of its flow lines, which I'll call threads, by virtue of the fact that it's divergenceless, these flow lines begin and end only on the boundary, and this norm bound says that the transverse density of the flow lines is also bounded by 1. In other words, they can't be packed more densely than 1 per unit area, okay, in their transverse direction. Okay, and then you have the following theorem given some subset of the boundary. Actually, this can be phrased more generally, but for our purposes, this is the application I want. Take some subset of the boundary, and in this cartoon, I've taken that to be an entire connected component. But in the next picture, it won't be an entire connected component. But just, it's easier to visualize that way. And it simply says that if you want to have as much flux as possible coming out of that boundary into your manifold, into the bulk, subject to the constraints above on the flow, that maximum flux will be equal to the area of the minimal surface in the same homology class as A. And I want to just clarify a couple of points. The minimal surface is usually unique, except at these phase transitions and so on, where maybe there's a couple competing minimal surfaces. On the other hand, the flow, the max flow, is highly non-unique. So these bit threads, if you want, they have a lot of room to move around, except on the minimal surface where the flow vector V has to equal the unit normal, or if you want, where the threads there are orthogonal to the minimal surface and maximally packed together. Okay? Elsewhere, they're very floppy. And I'll use this notation V of A to denote any max flow, okay, for a given boundary region A. And I just want to point out that what this does, I mean, this actually, Maxwell-Min-Cut theorem is used all over the place in computer science, essentially because it turns the problem of finding a minimal surface, which is sort of a nasty nonlinear problem with local minima and stuff like that, into a linear programming problem. Okay, well, I think it's obvious what I'm going to do next. Given this, I can just rewrite Ryu-Takenagi. And so this is the new version. As promised, surfaces do not appear anywhere in this version. I'm going to set 4g Newton equal to 1 for the rest of the talk. So now my entanglement entropy of A is equal to the maximum flux through A, which is also the maximum number of threads in the bulk that begin on A. Where do the threads go? They can end on A complement. If there's a horizon, they can end on the horizon. That's allowed too. And so the rules of the game are, first of all, that the threads cannot be packed more tightly than 1 per 4 Planck areas. So that's some law of nature. And the other is that the entropy is given by the maximum number of threads. Okay, so those are the 2 rules. From those 2 rules, you get Ryu-Takenagi. And you've automatically incorporated the homology condition and the global minimization. You don't have to put those in by hand. Again, the threads are very floppy, which means you can move them around in the bulk a lot. And in particular, you can move where they attach to A. And another thing you can do is that you can actually add threads that begin and end on A. Those, of course, don't count in the flux. And I'll come back to so these freedoms you have are some kind of gauge freedom, and they have a physical significance that I'll come back to. So if we just ask ourselves, okay, so to answer the question, what's the role of the minimal surface? The minimal surface, again, is the place where the threads are maximally packed together, so it's the bottleneck. So it's the place where if you want to know the entropy, which is given by the number of threads, you can get that answer just by looking at the area. You can count the number of threads anywhere you want, but if you don't know where the threads are and you just have the geometry, then a simple way to know how many threads you can put in is to get the area of the minimal surface. So it's essentially a calculational device. Okay? Perhaps this is obvious, but essentially it's an implementation of the holographic principle. If you want to know why is entropy computed by area, not volume, it's because bits are not stored in point-like objects. They're stored by one-dimensional objects. Okay, that's it. And now just, what replaces, so if we get back to the black hole case that I started with, what replaces this picture I found on Google image search? It's this one, where essentially, again, the horizon is the bottleneck, so that's where the threads are maximally packed together, but they're not located, the threads are not located on the horizon, okay? They're delocalized, which is what we wanted. And so my claim is that now this kind of delocalization is what solves the conceptual problems that I posed before. And so let's see how that works. Well, the first one is very easy, that you can easily show that even when the minimal surface jumps, when you have one of these phase transitions, the thread configuration is continuous. So if I change the region A, my thread configuration will change. It will always change continuously if I change A continuously. Now, the other ones had to do with having multiple regions. So let's just do 2 regions. And here, you have to understand that depending on what you're computing, you have different thread configurations. So if you're computing the entropy of A, you maximize the flux through A. If you're computing the entropy of A union B, you maximize the flux through A union B. You can't always maximize the flux through A and B, but you can show that you can always maximize it through A and A union B. That's a I'll call that the nesting property. Or, of course, you can maximize it through B and A union B. Okay? So a flow that maximizes the flux through A and A union B, I'll call V of A comma B. So if you want your first maximizing on A, and then within the ones that maximize on A, you maximize on B. Okay, so let's just do a simple toy example. Let's imagine that we had this kind of thing where the entropies of A and B were 2, but AB was 3. So we have 1 unit of mutual information and 1 unit of conditional entropy. And my little diagram would be like this, where I have 1 bit which is belongs to A, 1 bit that's shared, and 1 bit that belongs to B in this toy example. So what do my thread configurations look like? Well, I have 2 threads coming out of A. If I first maximize on A, I can have at most 2, and then I can have at most 1 coming out of B because the total can't be more than 3. Or I can first maximize on B, and then I have 2 and 1. Okay, and so it's pretty obvious what's going on here. So again, each thread here is a bit of A union B, and that bit in this simple example falls into one of 3 categories. It's either in A, in which case it's stuck here, that's this one that doesn't move, or it's in B, that's this one that doesn't move, or it can be in either one, in which case it's shared between A and B. So that's the unit of mutual information. Okay, so threads that are stuck on A represent bits unique to A. Threads that can be moved between A and B represent correlated pairs of bits. Now, of course, this example has no entanglement, so let's do one it's a little more exciting that has some entanglement. So I'm going to cut down my entropy to make my conditional entropy negative. So in this second toy example, I know that I have some entanglement. So now when I put my threads on A, I have 2 threads leaving A, but only one of them can leave A union B. So necessarily the other one goes to B. And same thing vice versa. Okay? So now we have a thread, in addition to the thread which can move between A and B, which represents this bit, which is classically correlated, I have a thread which joins A to B. This is a thread which is which does not represent a bit of A union B. But it is a bit of A, and it is a bit of B. By the way, these are qubits. I'm just not bothering with the Q part. So from this lesson, we learned that a thread that connects A to B, switching orientation depending on which one you're maximizing, represents an entangled pair of qubits. Okay? Now let's go back to what happens if I just have a single region. I had those freedoms to move the threads around or to add little loops. So if I just take this and divide it into 2 pieces, so I had like A equals A1 union A2, which I can always do, then we see that the freedom to move them between A1 and A2 represents the fact that there's a lot of correlation between A1 and A2, which we know is present in the field theory. And the freedom to add these little loops represents the fact that there's a lot of entanglement within A in the field theory, which we also know. Okay, so that's a lot of toy examples, pictures, words. Maybe you want to see some equations. So what follows is general. So you get a very nice formula for the conditional entropy in general, which is that it's the minimum flux on A subject to maximizing on AB. So that's the number of threads that are stuck to A that won't move off it. And the mutual information is the difference between that maximum and between the maximum, which is the entropy of A, and that minimum, which is also, so the difference between what happened to the flux between the maximum and the minimum, because I haven't changed the flux on AB, it must have gone to B. So that's the same as the flux that I can move between A and B. And again, that consists both of threads that leave A union B that I can move between them, and threads connecting A to B that switch orientation. Okay, and by the way, as sort of a technical dividend from this is the following. So normally in field theory, the mutual information for separated regions is a finite quantity, but to define it or to calculate it, you need to introduce a regulator, subtract the entropies, which subtracts off these area law divergences that one mentioned, and then what you're left with is what you're left with is something finite. But in this case, actually, you don't need to do that because you can define the max flow without a regulator, so you can actually define and calculate, in principle, the mutual information without ever introducing a regulator. Okay. So, and then finally, the conditional mutual information is the amount of flux that you can move. So don't worry, well, there's a lot of different ways of writing the mutual information in terms of other quantities. It's the amount of flux you can move between A and B, maximizing on C and ABC. So that's the equivalent here of this conditioning on C. And I just proved strong subadditivity because that has to be a positive quantity. And so we get a very simple proof of strong subadditivity. And the important point here is not the simplicity of the proof, but the fact that the connection to the information theoretic meaning of strong subadditivity, I think, is pretty clear. Okay? And that's the point I've been trying to make also about these other quantities. So that's what we're gaining from this picture. Now, one thing we don't have and that we really want is the information theoretic meaning of some of these special properties of holographic entanglement entropy, which include, for example, this monogamy of mutual information inequality, which we know to be true. We can prove it using the minimal surface prescription, but we don't really know what it is implying about the special properties in any conceptual sense of holographic states. And I think if we had, which we don't, if we had a flow-based proof of this inequality, that might get us some mileage in that direction. So that's an important open problem. Okay. Apparently I have time to talk about extensions, at least a few of them. So I have 3 extensions here to talk about. So first, just very briefly, emergent geometry. So given a metric, that implies a set of allowed thread configurations, but you can also take a set of allowed thread configurations on some manifold that doesn't have a metric, and you can, from that, derive a metric. The second is quantum corrections, which Juan talked a lot about. So Faulkner, Lukowitz, and Maldacena explained that the order G Newton to the 0, in other words, bulk quantum corrections to the entanglement entropy, are given by the entanglement entropy of the bulk fields between this region on one side of the minimal surface and the rest of the space-time. So you can reproduce that here by allowing, or I should say, I think you can reproduce it. I haven't done this quantitatively, so this is a preliminary idea. I think it can be reproduced essentially by allowing the threads to jump. In other words, you don't insist that they be continuous in the bulk. You allow them to jump where the number that are allowed to jump from one part of the bulk to another is determined by that bulk entanglement entropy. And then when you go to maximize the number, you'll get some that kind of tunnel through the minimal surface, and that'll, I think, reproduce this, this formula. Or you can think of them as kind of traveling through some kind of microscopic wormhole. So this is basically a concrete version of the ER equals EPR proposal. And then finally, covariant bit thread. So everything so far has been just the original Ryu Takenagi. We need a covariant version. And actually, it's very beautiful how it works out. So the covariant version of Ryu Takenagi is, instead of a minimal surface, you look for an extremal space-like surface in the bulk. And among the extremal ones, you find the minimum one, if there's multiple ones. And so what we need is a Lorentzian version of the max flow min cut theorem. This is not something you can just look up in some computer science textbook. And so we had to invent it. And it works out like this. It's very beautiful. So again, we have a vector field now in the full Lorentzian spacetime, again, divergenceless. We have to add this rule because there might be like a black hole singularity in our spacetime. The flux is not allowed to go in or out of the singularity, so those are not considered boundaries the way the conformal boundary of the spacetime is considered, where the flux obviously can enter and leave. And now we need something that replaces this, this norm bound. And what replaces it here is an integrated norm bound. So given any time-like curve, the integral of the norm of V, or rather the orthogonal projection of V, is less than or equal to 1. So in words, basically any observer counting threads through their lifetime adds up the total number of threads in their lifetime to be no more than 1 per 4 Planck areas. Okay, I don't have a good intuitive reason. This is just the rule that works, the rule that gives you the right answer. So now obviously we want to reverse engineer the meaning of this rule. And then you can prove, given these rules, this version of max flow min cut, that the max flow will be equal to the area of the, the max flow through what? I didn't say. The max flow not through A, but through the boundary causal domain of A, is equal to the area of the extremal surface, and actually is equal to the area of the minimal extremal surface. Just like for the original Ryutakinagi, this turns the problem of finding that minimal extremal surface into a linear programming problem, which I think might be practically useful. Okay, so this is version 2.0 of HRT. And how did it work? How did that theorem work? How could the threads possibly know what the area of the minimal surface is? Well, it's quite nice, actually. So in trying to get as many threads into the bulk as possible, leaving the causal domain of A, what you're going to do, there's no rule that says that the threads have to stay inside the entanglement wedge, but they will choose to stay inside the entanglement wedge because you can show that is how they will maximize the total number. So what they're going to do is they're going to stay confined to the entanglement wedge and then squeeze out through the extremal surface. And the number of them that's allowed will be equal to the area of that extremal surface, again, the minimal extremal surface. So this prescription actually finds the entanglement wedge and it finds the HRT surface. And here again you have a lot of gauge freedom, and now the gauge freedom is not just in the spatial directions, but also you can move the threads up and down the time direction. And in particular you can choose to, if you want, to put them all on a single Cauchy slice, in which case what you're doing is you're recovering Aaron Wall's Maximin version of HRT. Okay? But you don't have to do that. You could alternatively spread them out in time. Okay? And I think, you know, so given that this works, so this is the covariant version of bit threads, it would be nice to use it to derive some kind of deeper understanding of what's going on with the connection between information and geometry in this sort of covariant setting. Thank you.
Questions?
In the time-dependent case, did you consider trying to use a bivector instead of the vector field H, or equivalently a dual two-form?
We spent about a year considering it before we suddenly hit on the idea of just using a vector. Indeed, we wanted it to be a two-form with a leg in the time direction. And what we came up against is this problem that that's too global. I mean, we want to make it non-local, but that's actually too global because it knows everything about, if you want it to be divergenceless, you know, essentially you can think of it as being like sheets, like world sheets. And they continue forever, so they know everything about the future and the past of your space-time, and so it didn't work.
Does this thread have a physical meaning?
Where is this disembodied voice? Oh, yes.
Yeah, I'm here. Does this thread have a physical meaning, or is it an abstract concept that that is useful for calculations, or and have all these demanded properties?
Well, they're not physical objects in the way that a brain or a string is a physical object. But I think they are some kind of somehow a space-time in gravity is a representation of some state holographically. And this is like a step in translating between the geometry and the state. Is the thread configuration, or more precisely, the set of allowed thread configurations for a given geometry, is a way of decoding that geometry when trying to rewrite it as a state. That's how I would say it. But you shouldn't think of, they are not objects like a string or a brane or a particle is an object.
Okay, thanks.
Just to elaborate on that question, if you perturb the state on the boundary, then there's a perturbation of these threads as well. Is there, do you have a dynamics for those, the dynamics of the threads as you change the boundaries?
You mean in a time-dependent sense? I mean, there are two.
In a time-dependent sense.
In a time-dependent sense, I think it's a good question. Somehow, first of all, you don't want the threads to have to know everything that happens in the future, like what you might do later to the state. So if you have some happy thread configuration which obeys these constraints, and then later you do something to the state, it should still be okay. We know that property holds for the entropy, so we know that it holds for the actual area of the HRT surface. Now, maybe a slightly more interesting question is whether from the dynamics of the threads, you could, for example, derive the Einstein equation, and I haven't gone to that. But as I said, at least in the static case, there's a pretty straightforward way, given a set of thread configurations, to write down a metric. So that might be a first step in that direction.
So if your boundary area region A becomes bigger and bigger, eventually the minimal surface is going to hit the horizon and start to behave differently. How does your flow capture this change?
Yeah, so this has to do with the question of what happens under phase transitions more generally. Well, I'm not sure. Okay, I guess there are two ways to interpret your question. So one thing is that if part of the minimal surface is touching the horizon, then some of the threads are going to have to go into the horizon. So that means that some of your entropy is actually thermal entropy as opposed to being what is strictly called entanglement entropy, representing entanglement between A and A complement. So I think that was probably what your question was?
Okay.
I think there's one
last question.
If you consider this perturbed situation, let's say with a time-dependent perturbation, for example, a fluctuating horizon, would this type of picture match the entropy curve you would get from the hydrodynamics?
It's an interesting question. I haven't thought about that. It will match what you would get. Yeah, I guess I should say this. So it will match what you get from HRT. And HRT, as one explained, is a fine-grained entropy that is time independent if you're considering, let's say, the whole system. So if you have a fluctuating horizon, let's say you're throwing stuff into the horizon is getting bigger, but you're using HRT to compute the entropy of the whole system, you will find that never changes. So you will not capture the entropy production that occurs in that process. You can capture it by looking at subsystems, sufficiently small subsystems, and I haven't thought about in detail what the threads are going to look like, but they will give you whatever answer HRT gives you.
Okay, in view of the time, the rest of the questions can only be discussed later. So let's thank all the speakers of the morning for their excellent talks.